Dear students, resume back our discussion on video lectures of advanced digital signal processing. In the previous video lecture, we have seen how the upsampling and interpolation affects the frequency domain representation, and also how to apply filtering to the expanded signal to get back the original spectrum, okay, without having additional frequency components, and get an interpolated signal, okay, while doing so, right? So now let us see, as we discussed in the last class, if we now have a interest to change of say like fractional sampling rate conversion, how do we do that? Say for example, initial time period TB, say whatever, 1 by some 2000 or whatever. Okay, so now I would like to establish T dash that is equal to 1.5 times the capital T, right? That means I have an XC of T. Okay, I may apply this and get X of N, but now using this T dash, I would like to get a X dash of N, right? Another discrete time signal. This discrete time signal has the like the time period corresponding to T dash equal to T dash, or the sampling frequency, that is F dash, Fs dash. Okay, so initially we have a sequence that is sampled with a sampling frequency of Fs. Now we would like to have a sequence that should have a sampling frequency of Fs dash. These are important applications, and this Fs dash is not an integer multiple of Fs. Okay, it is not just like twice the Fs or half the Fs or 3 times the Fs. Okay, or 1 by 3 times the Fs. It is not an integer multiple. Okay, of Fs. Okay, so but we would like to have a fractional change sampling rate conversion from X of N to X dash of N, right? This application is also quite uh, like important and occurs many times. Say for example, if I have 8 kilohertz signal, okay, speed signal, I want to represent it for some like applications. Okay, so initially I might have recorded it, say 12 kilohertz. Okay, I have recorded it 12 kilohertz. Now I need for uh, listening to it, or for transmission purpose, I would like to convert it into 8 kilohertz. Okay, so then, so what's happening in between? So 12 to 8, if you want to convert, so what should I do? This is initial T, if you assume, and T dash is equal to, say, 2 by 3 times T, right? So sorry, frequency is 2 by 3 times, and then time period is 3 by 2 times. Okay, 3 by 2 times. Or if I consider this as Fs, and Fs dash is equal to 2 by 3 times Fs. Okay, yeah, right. And in some of the applications, it may be demanded by the codec, in which there is a fixed sampling rate in which it can only represent, or it can only store, or in some say when we transmit and we want to listen, there may be another device whose like sampling rate, operating sampling rate is different. Okay, again we may wish to transfer back to 15 kilohertz, for example. Okay, something like this. So for all these purposes, we need fractional sampling rate conversion as well, right? So now the question is, how do we change the sampling rate? Okay, by fractional fractional multiples of original sampling rate. Or similarly, how do we change the sampling period, which is fractional multiple of original sampling period? So what's the answer? Say for example, if I want to get T dash equal to 1.5 times T, so what do you suggest? So essentially, say I can write this as T dash is equal to, in this example, 3 by 2 times T. Okay, and hence I should ideally do, okay, downsample by 3 times. Okay, there are two operations that are required. Downsample by 3 times, and then there is another operation that is required, that is upsampling by 2 times. Right? As you can see, increasing the time period is through downsampling, means we are downsampling. Decreasing the time period means we are upsampling, right? And hence these are the two operations that are required. However, the question now is, among these two, okay, which is the first operation I should perform, okay, and then which is the second operation should I perform, okay? What is the sequence of the operations I should perform, right? These two are required to change the sampling uh, uh, rate or the sampling period. However, which is the operation? Is it upsampling should I perform first, and then the downsampling, or the reverse versa? What do you think? See, if the original spectrum is downsampled, then what may happen? The expansion will happen in the frequency domain, and hence there is a possibility of aliasing. Whereas if we do upsampling, then what, as you have seen here, okay, the spectrum will only compress, and then there is no, like, if there is no aliasing in XFN, and there will not be surely no aliasing and XGFN. Okay, also you may get actually additional the spectrum occupies lesser bandwidth than the original spectrum, right? And there is a possibility to upsample it more times than the original spectrum. For all these reasons, okay, we first perform upsampling and followed by downsampling. In any of the operations, wherever we want to do sampling rate conversion by fractional amounts, we first perform for all these operations. First, what we perform is, say, XFN. First, we would like to do upsampling, right, by 2 times here, okay, and then downsampling by 3 times, okay, to get actually X dash of n, right? So this is the sequence. Always first perform upsampling, then downsampling. But is that enough? Okay, so this, because this has no aliasing issues. Okay, no aliasing issues. Okay, if XFN has none. Okay, if XFN doesn't have aliasing issues, no, even the upsampling process doesn't have. And this also gives so better bandwidth for downsampling. But in between, what should we do? Okay, so I would like to, I don't want to write specifically this operation here, but I will write upsampling and downsampling here. Okay. Okay, first we do upsampling. Okay, and this is downsampling. Okay, but see, in addition to upsampling always comes along with what? So to get the, see, expanded signal is not good enough to for any of the real practical purposes. Okay, and additional spectrums that comes because of the compression are also to be avoided. Thus, upsampling followed by low pass filter is always comes as the, this is referred to as the, okay, interpolation operation. Okay, this is interpolation. Okay, so ideally, what should we do first? We should do interpolation first, and followed by, as you have seen in downsampling, see, we do not directly do downsampling, but we apply a low pass filter to anti-alias, or to get away with the frequencies that will anyway overlap when we expand by m times, okay, as an anti-aliasing filter. This process together is referred to as decimation. Okay, this process is referred as decimation, and this process is referred as interpolation. So for any practical reasons, What we do is, first we do decimation, first we do interpolation, right? Followed by decimation to get x dash of n. So what we do is first interpolation, okay, by 2 times, and decimation, okay, by anyway 3 times, right? So to expand this interpolation, now let us write each of the blocks. So, right? So if you want to change t dash equal to 1.5 times t, so let us start with x of n. What is the process of interpolation? So you should do now interpolation by 2 times and decimation by 3 times. So upsampling by 2 times, where every time upsampling filter comes along with low pass filter. Minus pi by where to where? See, upsampling by L times will give minus pi by 2, pi by 2. Here, minus pi by L to pi by L. And then here again a low pass filter. See, decimation has also 2 steps. That is anti-aliasing filter minus pi by 3 to pi by 3. Okay, and then downsampling. This is how we get x dash of n, right? So when you please note that interpolation alone. So let me write here explicitly. Okay, so interpolation alone, if we see what is the operation we have, say upsampling by L times and then filtering by low pass filter minus pi by L to pi by L. Okay, and this is x of n, whatever you give x of n, and this is x e of n, and this is x I of n, interpolated signal, right? Similarly, when we do decimation, okay, the process of decimation involves from x of n, first apply anti-aliasing filter minus pi by m to pi by m, okay, and then apply downsampling, because if you directly apply downsampling, there is a risk or possibility of aliasing, right? So these two operations now, okay, so are to be done together when you want to do sampling rate conversion, right? If you want to do sampling rate conversion, so interpolation, I will write the rate here by L times, I will write here for better understanding, by L times, and this is by M times. Okay, so interpolation means it has both the blocks of, say, upsampling and or expansion and avoiding the additional spectral bands, okay, other than the signal spectrum or the frequencies that are there in the originals, x of e power j omega, original spectrum, right? Similarly, decimation also has two blocks. One is applying a pre-low pass filter. This is referred to as anti-aliasing filter. This is anti-aliasing filter. Okay, and this is usually referred to as, okay, reconstruction filter. Okay, because this also this helps us to reconstruct the zeros in between, right? Or interpolate zeros, interpolation filter also you can call. Okay, so this is discrete reconstruction filter. Okay, right? So these two blocks has to be put together in when you want to do sampling rate conversion. Okay, so as we discussed, if we if we, which block to use first? Should we use decimation first or the interpolation first? Answer to that comes because of the which will affect the Nyquist rate more, or which will enable us to increase the band, to increase the sampling frequency, right? So interpolation always helps us to increase the sampling frequency and also doesn't affect the Nyquist rate, and hence uh, mm, it comes as the first block. After that, with proper filtering, okay, you have the provision for upsampling, you have the provision for decimation or downsampling, right? Yeah. So now let us see this. So then the next question is, okay, let us write for general sampling rate conversion. So if I want to change the sampling rate, T dash, okay, is equal to, say, L, okay, M by L into T. That is, I want to compress the signal, or by M times. The time period has to be increased by M times, and it has to be reduced by L times. Okay. So in this case, let us sketch now how should be the block diagram. Say XFN we have, and what should be the upsampling factor, and what is the low pass filter, okay, cutoff frequencies, and then what is the cutoff frequencies of this low pass filter, okay, and then what is the downsampling factors, and finally to get X dash of n. Okay, let us write these things. Okay, so this low pass filter, now this is the low pass filter is referred to as, okay, this is anti-aliasing filter. Okay, and this is reconstruction filter or interpolation filter. Okay, and this cutoff frequency for this low pass filter is from minus pi by what, L to pi by L, as we would like to cover the minus pi to pi spectrum in Xc of e power j omega, right? And this is upsampling by L times. Fine, because we want to reduce the time period by L. Okay, so this can be written as M into T into 1 by L. Okay, or say T by L into M. Okay, this is how you can write this better here. Okay, right. So, and then this low pass filter is from minus pi by M to pi by M. Okay, and this is downsample by M, right? And next dash of it. Now the question here is, okay, should we necessary to have two low pass filters? Okay, one for interpolation and another for anti-aliasing when we have a sampling rate conversion by a fractional factor. Okay, so the answer is no, not needed. Okay, you can effectively have a single low pass filter, and in that case the question is, what should be the cutoff frequency of the low pass filter? Okay, what should be the cutoff frequency of the single low pass filter? It should be, see, it should avoid the replicas in due to upsampling. It should also perform the anti-aliasing to limit the bandwidth before downsampling. Okay, so it has to be minimum of, its cutoff frequency has to be minimum of what and what? Pi by L and pi by M. Okay, this is the cutoff frequency of the low pass filter. So whichever is less, say if I'm performing upsampling only by 2 times and downsampling by 3 times, then I need to limit more during anti-aliasing, for anti-aliasing. So I will consider here, so pi by 3 is lesser than pi by 2, So I will consider this low pass filter cutoff frequency to be pi by 3. In other hands, if I am to avoid the replicas, say if I am doing upsampling by 4 times while doing downsampling by 3 times, then pi by 4 is lesser than pi by 3 and hence I will take pi by 4. So this is how the sampling rate conversion happens. Okay, this is the block diagram or the process of sampling rate conversion. Of discrete signal. Okay, so this encompasses all the things that we have discussed so far, right? So as an example, what I request you to do now is to let us go through a sequence where we start with x of e power j omega, because discrete time signal is given to us. And this x of e power j omega, from this x of e power j omega, assume that, so we have x of n here. Okay, from this x of n, we would like to get x dash of n. And this x of n has time period capital T, okay, which is sample from, anyway, this is sample from x of c, xc, like continuous time domain, xc of t. Okay, let us write this little space. Xc of t we have, and we have actually used sampling period t, ts, okay, initially to get x of n. And from this x of n, okay, my objective is to get t dash is equal to, okay, 3 by 2 times ts. Okay, let this be like this. Okay, and hence, so for performing this, what do? I will not do in single step. I will do it in 2 steps. So what are the 2 steps I do? I initially perform, okay, so to get this, what I do? I initially perform a upsampling, that is t1, t double dash, or say, so t up, I will say, is equal to ts by 2. Okay, so I will get actually x upsample signal, right? X upsample signal, okay, by 2 times. After I get this, what do? I will do the next step, that is I will perform downsampling of this. So let this x u of n here, okay, and I will perform downsampling now, okay, t whatever, t this is upright, dd is equal to ts, okay, tu into 3, okay, that is downsampling by 3 times. So I get here effectively finally x dash of n, okay. Okay, so this is what I would like to get. So now let us sketch the spectrums. So let the spectrums be, okay. So let us bring in the spectrums here. Okay, so this is x of, okay, let us not bother about xc of j omega. Xc of j omega you have anyway. Okay, from this assume that you have got here of through the sampling flow. So fs, you have actually x of e power j omega. Okay, let us start our discussion from x of e power j omega. And then you have applied, okay, this fs sampling frequency now becomes 2 times the fs, okay, upsample signal, right? You got x u of e power j omega. Okay, assume that we have taken care of interpolation and so on. Okay, now and then you up again x, we will take sorry, if d is equal to, okay, if s d is equal to f by 3 times, and you get this upsample signal. Okay, let us sketch these things. Let us start with, right. Okay, so let this be a 0 here, pi by 2. Let us take the same example for ease of understanding. Pi, 3 pi by 2, and 2 pi. Okay, let us go from up to here. Minus pi by 2, minus pi, minus 3 pi by 2, and minus 2 pi. Okay, and the spectrum, it be like this. Okay, this is the first term, and the second term is around 2 pi. Okay, and the third term is around minus 2 pi. Right? Okay, so and now let us, this is what we have sketched here, x of e power j omega. Sorry, e power j omega. Okay, and height, let it be 1 by t and so on. Okay, do not, we will not bother much about it, but let it be 1 by t. Okay, so now we would like to sketch first. What we want to do is upsampling. Okay, so upsampling has two terms. Okay, one thing is the compression of the spectrum. This is omega axis, compression of the spectrum. Second thing is filter. Okay, so what we wish to do is, okay, I will sketch both of them. Okay, for better understanding. Okay, let the base be with same. Okay, let this be here, and see, this now is expanded. So, and hence, so in frequency domain, it compresses minus pi by 4 to pi by 4. So it is, expansion is by, or the upsampling is by 2 times. And hence this 2 pi will come now. Let us sketch only from, sorry, 0. This is pi by 2, and this is pi. Okay, so this is pi by 2. Let us directly sketch pi. This is pi. Okay, and minus pi. So hence, let us sketch here around this, right? And this one comes here. Okay, we will not bother now about the other regions. Okay, this is W dash equal to 2 into W. Okay, because compression has happened. Okay, it's not 2 into W. You can see that this axis itself is 2 into W. Okay, right. That means, yeah. So essentially, this is x of, rather than writing here 2 into W. So x of e power j 2 omega. Okay, this is how we can write. So L omega. That's what is here, right? And then you can write this as omega dash axis. Okay. So now, yeah, okay, right. So now what we want to do is, we want to apply spectrum or the low pass filter. Sorry, we want to apply low pass filter to avoid these repeating patterns. Okay, so let us apply low pass filter. Yeah. Okay. So the low pass filter has to span the region. Okay, minus pi to pi here. Okay, roughly it has to cover this region in the x of e power j omega. Okay, so to do that, what should we do? So let me write here as well the intermediate things. Okay, so rather than directly jumping on to the no, so here let us write xe. Okay, so that we have the process clear. Okay, xe of n, xe of e power j omega. Okay, xe of e power j omega, and after that we get actually okay xi of e power j omega. Okay, and what we wish to do now is instead of applying two spectrums or two filters, we would like to apply a low pass filter which is having minimum of pi by l comma pi by 3. Okay, so and this we call it as intermediate. So this is filtered. So this let it be writing x I of e power j omega, sorry, x I of n. Okay, and this is x f of n. Okay, for our notation, and x dash of n. So we would like to get now what we want to get here is okay filtering. So from here we want to do apply low pass filter. Okay, low pass filter of what? Minimum of okay pi by m l comma pi by m. Okay, through this process what we get here is x f of n, or in this here same thing happens, and through this what we get here is x f of e power j omega. Okay, and here the low pass filter explicitly writing the low pass filter cutoff frequency. It is low pass filter of cutoff frequency omega c is equal to pi by what 3 here, because that is the minimum of pi by l comma pi by. So now let us apply that filter. So pi by 3 is from where to where? So pi by 4. So here, okay, so you have here minus pi by 3 to pi by 3. Okay, so now the spectrum looks like this. Multiplication with low pass filter of this gives us the spectrum that is non-zero from minus pi by 4 to pi by 4, and and eliminates the other frequency components that are not there in the original signal. Okay, and if we had applied a low pass filter similar to upsampling process, then we would have applied from minus pi by 2 to pi by 2. Okay, so that also would have eliminated, but in this case it doesn't make much difference. But however, if these frequencies in the original signal are from minus pi to pi, then it would make a difference. Okay, so here we apply from a spectrum from minus a low pass filter from minus pi by 3 to pi by 3. Okay, with a gain of how much? See here, I have not written the gain here, but how much should be the gain? With a gain of what? L here, because this low pass filter is gain. Okay, here it is gain L, and at gain how much? Gain M. Okay, low pass filter in anti-aliasing filter has anti-aliasing filter has unit gain. Okay, with gain 1. Okay, so both multiplied. So two filters in cascade is like in frequency domain, just multiplication. So its gain is L. Okay, so its frequency, its now magnitude here is L by T, whereas here it is 1 by T. Okay, and this please note that okay, this is with gain L. Okay, right. So and hence now what we should do for this to get the signal back, or to get the complete change of sampling rate, to what we should do is we should have here a downsampling operation. Okay, T by Tu into 3. Okay, similarly, you should have a downsampling by 3 times here. Okay, so to get xd of e power j omega. Okay, or x dash of e power j omega rather, right? X dash of e power j omega. Similarly here, we should have you should get actually x dash of n, right? So this operation now, you can also represent here. Okay, just we represent by, sorry. Okay, we represent by upsampling by 2, no, explicitly here. Okay, right? So now we will sketch this to complete this discussion. Right, and then this is 0, and we should now what should we do? See, if this after filtering, you can see that minus pi to pi, this is whatever we have sketched is correct. But what would happen is, because this is a discrete time Fourier transform, what do you think will happen? There is a repetition at 2 pi. Okay, so which is not shown here, but there is a repetition at 2 pi. Okay, so at 2 pi, okay, you would see that the same spectrum appears. I have not sketched it, but it will be there. Okay, similarly this side, right? So now when we expand, what shall happen? What should happen? So the spectrum now will also expand. By how many times? 3 times we have to do this. So it expands from where to where? So this is pi by 2. So this is minus 3 pi by 4. Okay, slightly higher than pi by 2. And similarly, this is 3 pi by 4. Slightly higher than pi by 2. Okay, similarly around 2 pi, also 2 pi plus 3 pi by 4. Okay, and then 2 pi minus 3 pi by 4. So you will have a spectrum. It's from here to here. Okay, similarly another replica of the spectrum from here to here, right? Similarly, you will have actually at here, if we would like to sketch, okay, at 2 pi you will have another spectrum, right? So another right, this also get expanded by 3 times, and hence around minus 2 pi you will have right. So 2 pi minus 3 pi by 4 to 2 pi plus 3 pi by 4. 2 pi minus 3 pi by 4 to minus 2 pi plus 3 pi by 4. Okay, so I think we have given, yeah, I think it's fine, right? So this is what is the spectrum you get. And if you see in the range minus pi to pi range, what you see is this. Okay, minus pi to pi range. You have seen the same signal with the same signal content, but the spectrum having having the frequency that is corresponding to 3 times higher, but 3 by 2 times higher than the original signal x of n. Okay, so this will have now fs dash is equal to 3 by 2 times fs. Okay, that's what happens. Or t dash is equal to 2 by 3 times sorry, fs dash is equal to 2 by 3 times fs. Okay, and t dash equal to 3 by 2 times t dash t. Okay, this is yeah, this is what how the sampling rate conversion by fractional rate can be done. So we apply downsampling, or we apply first upsampling, followed by low pass filter, and then downsampling to get the sampling rate conversion, right? And these are all in time domain, and you can see these are all in frequency domain. Fine. And in minus pi to pi range is what it repeats, and finally it is of the amplitude, okay, L by capital L by T. Okay, fine. This L by T is with respect to the magnitude it has in continuous time spectrum. Okay, so if you see this continuous time spectrum, if you see sketch it, okay, it will have the spectrum with some magnitude, and if it has unit magnitude there, then it is L by T magnitude here, right? Okay, so this is how this sampling rate conversion by fractional factors can be done. Thank you. What I request you to do is you take now a spectrum, okay, as an example, homework, okay. Let the spectrum x of j omega, xc of j omega has this spectrum. Okay. Okay, so this is 2 and this is 4. Assume that, just I think in into 10 power 4 or whatever. Okay, don't bother about 2k and 4k. Okay, they are the heights, and this is minus 5, say minus 1k h and 1k h. Okay, this is in omega pi, omega by 2 pi. Okay, for this, what I suggest you to do is, so how will be the spectrum of the sample signal x of e power j omega if we sample this, okay, at t is equal to 2k, okay, and t1 equal to 2k, and t2 is equal to 4k. Okay, case 1, and this is case 2. Okay, so now what we wish to do is, from this x of n, you will get actually, this is actually x of t, right? xc of t. Okay, from this either of these two, when we do, we will get x of n. From this x of n, okay, what we wish to do is say downsample it, or I will give as independent problems. Okay, sketch the spectrum of decimated sequence, okay, with decimation factor of, okay, of decimation factor of 2 in case 1 and 2. Okay, so this is what is expected first. Then sketch the spectrums of interpolated. So interpolated means expanded followed by filtered. Whole thing is there. Sequence with interpolated factors of, okay, again 2 in case 1, okay, and 2. Let me be for 2 as well. Okay, and further sketch the spectrum of sequence having sampling rate. Okay, sampling rate 3/2 times original sequence. Okay, that is fs equal to, okay, fs dash equal to 3/2 times fs. Okay, for original sequence in case 1 and 2, right? So design necessary filters in between, okay, for each of these processes. Sketch block diagram and design necessary filters in each, okay, of these, okay, in each of these problems. Okay, so and what I suggest is let us have a slightly different spectrum. So this is xc of j omega, one instance of xc of j omega, and let us have for us another xc of j omega. 0 here. And okay, this is minus pi to pi. Okay, so it is like I have sampled and given, so otherwise we can take it as, so here you can take it as let us have a symmetric spectrum. Same example as before. Okay, same example as before. 1k to 1k. Okay, it's just that the frequencies are now changed. Okay, let this be some 4k height. Okay, this is one example. Let this be question 1 and this be question 2. Okay. So you can do question 2 first if you feel that it is almost similar to the original, like our discussion, and then you can get back to question 1. Right? There is a good aliasing that may happen, but try to sketch in each of these cases what will happen. Thank you.